Now, as we know, people usually talk to communicate, consisting of the same particles that left the speaker's mouth. So how fast does sound go? So different media are made of different materials. Today we're going to be talking about sound waves. So now that we've learned some of the basics about how waves work and what their properties are and how to draw them, we can look at a particular example of a wave. And the sound wave, as we'll see, is a fairly important wave out of all the waves that we could be looking at. So to begin with, we'll be talking about properties of sound waves. Things like why they're important, and their sort of frequency, amplitude, that sort of thing. Now, as we know, people usually talk to communicate. I'm doing it right now, after all. And the thing about speech and talking, it's an application of sound. Speech travels in a sound wave toward your ear or toward a microphone, and that gets translated into electricity or into electrical signals for your brain to interpret, and they're eventually figured out into words and sentences and structures and that sort of thing. So we can see that without sound waves, we can't make that initial communication. So we can't pick up the words or the sentence or anything. So right away we can see that sound is a pretty important part of our lives most of the time. So what is sound? Well, using the terms that we've learned about before, I can tell you that it's a longitudinal mechanical wave. That means that the particles vibrate in the same direction as the wave travels, and mechanical means that they're doing it by colliding with each other, as opposed to interacting with, electric fields or something like that. So it's transmitted by the collision of particles in the medium, and that's usually air particles. So sound travels through air most of the time. So the wave can be thought of as a series of compressions of air particles. So because the particles are vibrating in the same direction as the wave is traveling, there'll be some parts of the wave where the particles are close together and some where they are far apart. That's a feature of all longitudinal waves. So remember that when a wave travels, the particles themselves aren't what are transmitting the energy. We can see, for example, in this wave, that the wave is propagating from left to right, but each of the particles stays in the same basic position. In a longitudinal wave, the particles move back and forth instead of up and down, but they don't carry the energy of the wave with them. They simply pass it on to the next particle. So once again, this is a feature of all waves, not just sound. Waves are a way of transferring energy without transferring matter. So sound waves that reach your ears are not consisting of the same particles that left the speaker's mouth. Instead, they're consisting of the air particles that were already right next to your ear, that have just been knocked around by the sound waves that came out of the person's mouth. Does this make sense? So their voice irritates air particles near their mouth, and that sets up a wave which causes more particles to vibrate, and eventually that wave of vibrating particles reaches your ear and vibrates the air there, and that's the sound that you can hear. So the sound wave propagates through the air. That's the term that we give when a wave is traveling. It can sometimes be a little misleading to use the word traveling because there are no particles that are traveling, only energy. That's why instead of using the word travel, we use the word propagate. So how fast does sound go? Well, it depends. It turns out the speed of sound depends on how particles in the medium interact. As I said, that's usually air, but air can be different temperatures or different densities, and that can affect how fast sound travels through it. We can see a photograph over here of an aeroplane moving at the same speed as sound in air. So the speed of sound varies based on the spacing between particles in the medium, so how close together they are, and how well they rebound off each other, so what the medium is made of. And so we call these two properties density, how close together things are, and elasticity, how well it can rebound and react. And both of these have a large effect on how quickly sound will travel through a medium. Even air can allow sound to propagate at different speeds, if it's at different temperatures, for example. So different media have different densities and different elasticities. And of course, most of these are very different to those of air. You can see a photograph here of plural of medium. So different media are made of different materials. So sound will tend to travel through denser materials more quickly. That means that if we look at your typical solid, then sound waves will travel through that solid more quickly than they will travel through air, simply because the particles are much closer together. So we have a table here of the speed of sound in various different media. First we have two gases, air and helium. We can see that the speed of sound in air is about 343 meters per second. So that means that every second, a sound wave can propagate across 343 meters of air. This is assuming that we're at standard temperature and pressure, that is 25 degrees Celsius at normal 1 atmosphere pressure. So now let's take a look at some liquids, mercury and water. As you can see, because liquids are so much more dense than gases, sound waves will travel far more quickly. So these speeds are about 1,500 meters per second, which is 4 or 5 times faster than the speed of sound in air. So we can see that in liquids, sounds will travel much more quickly. That means that if you're underwater and you hear a sound, you'll hear it more quickly than if the source of the sound was above water, and so are you. Because if both the source and you are above water, then the sound will propagate through air at a relatively slow 340 meters per second. But if you and the source are both underwater, that means the sound wave will propagate through the water at a much faster 1,493 meters per second. Alright, so how about some solids? We can see that most of these solids have a propagation speed that is even faster than mercury and water. So of course, metals will have different densities, usually greater densities, and also different elasticities, which explains why there's so much variation between them. In general, the harder solid is, the more quickly it will allow sound to propagate. So we can see right at the bottom that sound will propagate through diamond at a speed of about 12 kilometers per second, which is far faster than for any of the other media here. Alright, so that concludes the theory for this section. We've talked about the speed of sound, exactly what sound is and why it's important. So let's go on to some questions.